analysis. In the first lecture, we have discussed about the significant digits. Let us recall what is significant digit. Significant digits. Okay. Suppose x is any real number that can be written as 0.A1, A2, A3, An, and so on into the floating point representation like that, where A1 is not equal to 0, then this form is called normal form. Normal form. Okay, and the term in the bracket are called mantissa. Then if we are writing approximation to x, that is suppose floating of x up to n digits, then we can write it A1, A2, A3, An into 10 raised to power e. With A1 is not equal to 0, then we'll say the number of digits in mantissa are called the significant digits. So number of digits in mantissa are called significant digits. Significant digits. Okay, so whenever you want to find out the significant digit in a number, then write the normal form of the number, and then the number of digits in mantissa are called significant digits. Okay, so there is one result on significant digits. The number x star is what? It is nothing floating of x. X star is said to approximate x to n significant digits, or figures if n is the largest non-negative integer for which relative error x minus x star upon mod of x is less than equal to 5 into 10 raised to power minus n. So this x star approximating x to n significant digit if relative error is less than equal to 5 into 10 raised to power minus n. So n is what? That is the significant digit. Significant digit. Okay. So let us explain it with the help of one example. Let the number x equal to pi, and you know the value of pi, it is having finite digits 5, 9, 2, 6, 5, 3, 5 and so on up to infinite. Then let us find out the x star up to taking 3 digits into consideration. Okay, so x star is what? 3.14. So x star is the approximation to x, or x star is the approximation to pi. Then x minus x star is equivalent to what? 0.00015926 and this is what? Approximate error. Relative error is what? E of a upon mod of x, that is this value. It is nearly coming out to be 0.00051 and so on. Okay, this number is less than, this is what, 0.00051. Okay, this number we can write it as less than 0.005. There are 3 0 and here it is 2 0 obviously. So this number is less than 0.005. We can write this number as 5 into 10 raised to power minus 3. So we can say x minus x star upon mod of x is less than or equal to 5 into 10 raised to power minus 3. Whenever x star we are taking up to after decimal 2 digits, then it is coming out to be 5 into 10 raised to minus 3. So what does it imply? That x star approximating x to 3 significant digits. 3 significant digits. Also, we know from here we can write 0.314 into 10 raised to power 1. Okay, so here this is Manteser and number of digits in Manteser are what? Significant digits. This is 3. So this is verifying from here. Okay, so x star approximating x to n significant digits whenever the relative error is less than equal to 5 into 10 raised to power minus n. Here n is what? That is 3. Okay. Next is arithmetic operation. Arithmetic operation. Let floating of x, floating of y are approximation to x and y, then addition, subtraction, multiplication and division. These symbols represent machine addition, subtraction, multiplication, machine multiplication and division. We can express as x plus y is equivalent to floating of x plus floating of y. That means whenever we are adding two numbers with the help of computer calculator, then it is equivalent to floating of x. That means approximation of x plus approximation of y, then their sum is also approximated, how many digits that computer or machine can carry. Similarly, x minus y, floating of x minus floating of y. X multiplication y, floating of x into floating of y. X division y equivalent to floating of x divided by floating of y, then their approximation. Okay, let's do one example. Suppose that x equal to 5 by 7 and y equal to 1 by 3. Suppose two numbers are given to you, x equal to 5 by 7 and y equal to 1 by 3. Then use 5 digit, 5-digit chopping for calculation x plus y, x minus y, x into y, multiplication of between x and y, and division. So in order to compute the value of summation, addition, subtraction, multiplication and division, use chopping with 5 digits. Okay, let's do addition. X equal to 5 by 7, that is 0.714285, and so on. And y is 1 upon 3, that is 0.3333. It is going up to infinite. Since we have to use 5-digit chopping, so 1, 2, 3, 4, 5. So what we have to do? We have to chop this series after 5 digits. In y, also we have to do that. Okay. So floating of x is what? 0.7142 and floating of y is 0.335 digits. Then we are finding addition with the help of calculator. Then it is coming out to be floating or with finite digits. Then floating of x plus floating of y. Floating of x, floating of y. That is 7.428 plus 0.33. It is coming out to be floating of 1.04761 into 10 raised to power 0. Okay, we can express like that. Okay, now how many digits in this number? 1, 2, 3, 4, 5. So obviously 5 digits we have to truncate the series. It is coming out to be 0. It is what? 1.04761. So the result is coming out to be here 0.10476. This is the standard way to represent now. That is what? 1. So x plus y is coming out to be this. Similarly, we can compute the value of x minus y, x in multiplication y. So let us write in table. You can verify result from here. Result, actual value, actual value, absolute error, relative error. Let us find out the operation x plus y that we have already done. That is 0.10476 into 10 raised to power 1, and its actual value is 22 upon 21. Okay. If you see from here, we'll find out actual value. X is what? This number, and y is this. So x plus y is what? 5 by 7 plus 1 by 3. It is 22 upon 21. So this is the actual value. If we find out error here, so error will be what? Absolute error. That is true value or actual value minus approximate value. So what is this true value? Means actual value. Okay, so that is equivalent to what? 22 upon 21 minus approximate value is what? 0.10476 into 10 raised to power 1. This is coming out to be 0.190 into 10 raised to power minus 4. And relative error, so this is what? This is your absolute error. 22 upon 21, that is the actual value, and this is the approximate value that we computed by using chopping. Okay, then the difference is coming out to be this. Relative error. Relative error is what? Actual value minus approximate value upon actual value. So this is already computed, that is equivalent to this value, 0.190 into 10 to the power minus 4, that is the absolute error. So 0.190 into 10 to the power minus 4. And the actual value is what? That is 22 upon 21. Result is coming out to be 0.182 into 10 raised to the power minus. So this is your relative error. So absolute error in the previous case we computed, that is 0.190 into 10 raised to the power minus 4, and the relative error is what? 0.182 10 raised to the power minus 4. Similarly, we can compute the value of subtraction, that is x minus y. Okay, it is coming out to, you can do it by yourself, just I am providing you tables so that you can verify your result. Okay, 8 upon 21, 0.238 10 raised to the power minus 5, and 0.625 into 10 raised to the power minus 5. So this is the absolute error and relative error. Similarly, for multiplication, you are getting value as 0.23809 into 10 raised to the power 0, and actual value is 5 upon 21, and absolute error is 0.524 into 10 raised to the power minus 5, and relative error is 0.220 into 10 raised to the power minus 4, and division is 0.21428 into 10 raised to the power 1, it is 15 upon 7, 0.571 into 10 raised to the power minus 4, and relative error 0.267 into 10 raised to the power minus 4. So you can verify results by yourself. Okay. Next is, if you compare just result, like these are all operations we are using: simple addition, subtraction, multiplication, division. Here we are getting all these values after applying these operations using chopping, that we have already discussed, and these are the actual value, absolute error, that we computed as we have done in this example. Okay, so verify your result by doing calculation by yourself. Next is loss of significance. Loss of significance. What is loss of significance? The most common error producing calculation involve the cancellation of significant digits due to subtraction of nearly equal numbers. That means what? Suppose you are having two numbers. Suppose let x and y are real numbers. Let x and y are real numbers. Okay. With x is greater than y, have k digits. So the form of x and y will be what? Then floating of x will be what? That is having k digits, 0.d1, d2, let us suppose it is having k digits, then floating of x will be d1, d2, d3, dp, alpha p plus 1, alpha p plus 2, alpha k into 10 raised to power n, and floating of y 0.d1, d2, dp, beta p plus 1, beta p plus 2, beta k into 10 raised to power n. Okay, let us denote this number by x and y only, no need to write it in terms of floating of x, floating of y. Just take this is x and this is y because it is having k digits. Okay, so x and y are real number having k digits, and x and y are nearly equal number with the condition x is greater than y, that is already given. Okay, whenever we subtract y from x, what we are getting? These p digits in x and y are same. So what we'll get? We'll get 0. This number minus this number. We are getting alpha p plus 1, alpha p plus 2, alpha k minus beta p plus 1, beta p plus 2, beta k into 10 raised to power n minus p. Okay, we can write it like that, or we can write it the whole thing as gamma p plus 1, gamma p plus 2, gamma k, 10 raised to power n minus p. So x minus y has k minus p significant digits. Means what we explain here. X is a real number having k digits. Let us suppose d1 is not equal to 0. Okay, and y is also like that, d1 is not equal to 0, it is in normal form. So how many significant digits in this number? It is having k significant digits in both the number. So there are k significant digits in x and y. But whenever we are x and y are nearly equal and we are subtracting this number, then what we are getting? We are getting k minus p significant digits in x and y. So what we got? We got loss of significance in the subtraction of nearly equal number. So how much loss of significance? K minus p. Only how many digits are lost? P digits are lost. Okay. So x minus p, y have k minus p significant digits. Okay. Whenever we are doing calculation with finite digit arithmetic, and sometimes due to loss of significance we get error in our calculation. How we are getting this kind of error? Let us explain it with the help of one example. So one more thing I should write here. Let's example. Let p equal to 0.54617 and q equal to 0.5461601. Use 4-digit arithmetic to approximate x p minus q and determine the absolute and relative error using rounding. Okay. So there are P and Q, two numbers, they are nearly equal. If we see in P and Q, they are having a starting three digits same. Okay. So what we have to do, we have to compute subtraction of P and Q. So P equal to what? That is 0.54617 and Q is 0.54601. So here you are having these three digits same between P and Q. So we can say P and Q are nearly equal number. Okay. So we have to approximate P to 4 digits. So P star will be what? 1, 2, 3 to 4 digits. So it is 0.5662. Why? Because rounding we are using. Okay. And Q star will be what? That will be 0.5460. Okay. So now find out exact value of the subtraction P minus Q. This is 0.00016 and find out approximate value of the subtraction, that is coming out to be 0.0002. So if you see in the exact value, it is having two significant digits. And here we are having one significant digit. We are noting it as here. Okay. So in R star we are having one significant digit, in R we are having two significant digits. If suppose we have to use only three in calculation, three digits, so R star is coming out to be 0. But actually the value of the subtraction between P and Q is not 0. So due to that, wherever we'll use P minus Q in further calculation, it will give you 0. So a huge error may produce due to loss of significance. So whenever you are having the nearly equal number, then loss of significance may create problem whenever we are subtracting nearly equal number. Okay. So we are getting loss of one significant digit. Okay. So due to that, it will create error. Let us compute the value of absolute error, that is R minus R star. That is coming out to be what? 0.16 minus 0.0002. It is 0.00004. And relative error is coming out to be E of A upon R, mod of R, that is coming out to be 0.25. Okay. So there is a big difference between the errors. Absolute error is coming out to be 0.0004 and the relative error is 0.25. This is a large error. So whenever we are using finite digit arithmetic and subtraction occur between two nearly equal numbers, then loss of significance may occur and it may create error in our further calculation. Okay. So let us see some more example where loss of significance may create problem. Let us take one example. Compute under root x plus 1 minus 1. Whenever x is nearly equal to 0. Okay, let us take the value as 1.2345678 into 10 raised to the power minus 5. Okay, use 8-digit rounding. Next is rewrite the expression to avoid the subtractive cancellation. Okay, so undoubted, but we have to compute the value of undoubted x plus 1 minus 1. So we have to compute the value of undoubted x plus 1 minus 1. So x is given to you this value. So it is containing how many digits? 1, 2, 3, 4, 5, 6, 7, 8. 8 digits. Okay, so 1 plus x. So first compute the value of 1 plus x. It is coming out to be what? 1 plus 1.0000062, and its square root value, how many digits? 1, 2, 3, 4, 5, 6, 7, 8. Okay, so the value is coming out to be 1 plus x. I have done some mistake, let me check. 1 plus 0.00001, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So it is coming out to be, after this is the value, 1.00001, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8. Okay. So this value is what? If we take the square root of 1.0000123, the value is coming out to be 1.0000617. Okay. How many digits we have to take into consideration? 1, 2, 3, 4, 5, 6, 7, 8. Okay, so it is coming out to be what? So it is up to here. So the value is coming out to be 1.0000062 rounding. Okay, so undoubted 1 plus x minus 1, it is coming out to be 0.0000062. It is having 8 digits. It is having 8 significant digits. If we see in this undoubted 1 plus x. Okay. But now when we subtract 1, actually this number undoubted 1 plus x is also nearly equal to 1. So when we subtract undoubted 1 from undoubted 1 plus x, then loss of significance occurs. So how many significant digits we are having here? We are having only 2 significant digits here. So loss of significance occurs. If we are taking only 4 digits in our calculation, then the expression value will be what? It will be coming out to be 0, and there is no reason to compute this value. So in that, so whenever there is a subtraction of nearly equal numbers, then we should try to avoid subtraction sign between the nearly equal numbers, because whenever we will subtract nearly equal numbers, so the loss of significance occurs. So what we do in that case, will try to avoid subtraction sign. How we can avoid this subtraction sign? So in order to fix it, so to fix it, what to fix this problem? Whenever we are losing loss of significance, what we should do? We need to rationalize this expression. Why? Because there is a subtraction sign and will multiply. So to fix it, rationalize the expression. Why we are doing so? Let's see. Under root 1 plus x minus 1 will multiply it under root 1 plus x plus 1 upon under root 1 plus x plus 1. What is coming out to be? It is coming out to be 1 plus x minus 1 upon under root 1 plus x plus 1. It is cancelled, coming out to be x upon under root 1 plus x plus 1. So now we are not having subtraction between the nearly equal number, because this expression under root 1 plus x and 1, they are nearly equal numbers. So there is no subtraction sign, so will not get loss of significance. So x upon under root 1 plus x plus 1. Actually we are getting the different form of the function where subtraction sign doesn't exist. So what would the value in this case? It is already, we have already calculated the value of under root x plus 1. Just put the values of x and under root x plus 1 etc., and then after computing we are getting result as 6.1728199 into 10 raised to minus 6. Okay, so this is the value of the function. But in the previous case, due to loss of significance, that function value may vary. Okay, one more example we are taking here. The quadratic formula okay, before that I should write only the example, the next page, because okay, find example. Find the roots of the equation, the quadratic equation. What is quadratic equation given here? X square plus 62.10x plus 1 equal to 0. Find the roots of the equation using 4-digit rounding. Actual root are given. Actual roots of the equation are 0.0161, 0723 and minus 62.08390. Okay, these are the two actual root of the equation. But we have to compute root of this equation using 4-digit rounding. Okay, let's do it. You know how to compute root of the quadratic equation? Suppose the quadratic equation is ax square plus bx plus c. General quadratic equation. Okay, then if we compare this with the given equation, okay, so a is what? 1, b is 62 point, c is 1. Okay, formula to compute roots of general quadratic equation is x1 equal to minus b plus b square minus 4ac upon 2a, and another root can be computed with minus b square minus 4ac upon 2a. Okay, now just put the value of a, b, c into this formula and compute the value of x1 and x2. Now x1 will be minus 62.10 plus 62.10 square minus 4. A is what? That is 1. We have to use 4-digit accuracy, so we can write it 1.000 into 4ac, 1.000. This is the actual procedure. A is what? That is 1.000. Okay. So what is the bracket? This square root term we are getting. So just compute all the term in the square. That is 62.10 square. That is coming out to be 38. That is equivalent to what? B square. Okay, 3856.410. Since we have to use here 4-digit rounding, so we'll take it as 3856. Okay, what is the value of 4ac? The value of 4ac is 4.000. Okay, so b square minus 4ac is 3856 minus 4.000. It is coming out to be 3852. Put it. So square root of b square minus 4ac, it is coming out to be 62.064482. 4-digit. So 62.06. Okay. So x1 equal to minus b plus b square minus 4ac upon 2a. It is what? Minus 62.10 plus 62.06 that we computed here upon 2.000. Okay, so the value is coming out to be minus 0.04 upon 2.000. The value is coming out to be minus 0.02. This is x1. Okay, we are getting here poor approximation to the exact root. Exact root is given to you here, this 0.01610723, and here we are getting root this. So why it is happening? Because of subtraction between nearly equal numbers. This is a negative number 62.10 and this is a positive number, so subtraction occur between nearly equal numbers. So these two numbers are nearly equal, so we are getting the value of the root is what? Minus 0.02, and this is not a very good approximation to one of the exact root. So what we do in this case, we'll try to avoid subtraction sign between the nearly equal number. So for that, so how we can avoid it? We'll use rationalize. Okay, we'll rationalize this formula so that we'll be able to reduce or avoid subtraction sign. Before that, one more thing, if you want to check error at this position, so what we can do, we can just compute error, relative error. Okay, so exact root here is what? Minus 0.016111, and approximate root minus 0.02000. So what would be the relative error in this case? It will be minus 0.016111 minus plus 0.02000 upon minus 0.016111. It is coming out to be 2.4 into 10 raised to power minus 1. Okay, so this is the error we are getting, relative error. That is a big error, 0.24. It is not a very small error. Okay, on the other hand, one more thing, we can compute the root for another way also. Like this is one root, another root x2. Compute x2. x2 is what? That is minus b, that is minus 62.10 minus 62.06 upon 2.000. The value is coming out to be, after computing, minus 124.2 upon 2.000 minus 62.10. Okay, this is the another root x2, and the actual root is what? That is minus 62.08390. So this x2 is close to the actual root. Here if we will find out relative error, then we are getting here the relative error is coming out to be minus 62.08 minus 62.10 upon 62.08. If we are taking only the 4 digits, then it is coming out to be 3.2 into 10 raised to the minus 4. Approximate error. Actually, we are not using all the digits. You should use all the digits, then also you will get a small error. If we compare from this error, here the error is what? 0.24. But for the second root, we are getting error, that is 0.00032. So it is a small error in comparison to the previous case. So that means there is a problem with this root. So what we should do? We should find the modified root. So what we do to obtain a more accurate 4-digit rounding approximation for the root x1, we change the form of the quadratic formula. Why? Rationalizing the numerator. Okay, so what we do? x1 equal to minus b plus b square minus 4ac upon 2a, multiply it, minus b square minus 4ac. So it is coming out to be what? Minus 2c upon b plus b square minus 4ac. So now that subtraction sign convert into the addition sign. So that loss of significance occurs, that will be reduced. Okay, so x1 is coming out to be what? Now compute x1, that is minus 2 into 1.000 upon the value of b is 62.10 plus 62.06. The value is coming out to be minus 0.01610. Here we will find out relative error, exact value of the root x1 minus approximate value. So So this is, we can say, modified, right, x1. Okay, so here iterative error we are getting as 6.2 into 10 raised to the minus 4. Verify it by yourself. That is a small error. Okay, so just keep in mind, whenever you are getting subtraction between nearly equal number, as we got in this case, they are almost nearly equal number and subtraction sign occur between these, then we should avoid this situation and we'll try to avoid subtraction sign between the nearly equal number. If possible, then we should find out the way how we can avoid that subtraction sign. Okay, so just keep in mind, whenever b is positive, if you see here in the equation, in this equation, b is positive, so we are getting formula, this formula. Okay, so whenever b is negative, then you are getting formula to compute the root, that is minus 2c upon b minus b square minus 4ac. When b is positive, as in our case, we are getting b equal to minus 2c upon b plus b square minus 4ac. So just keep in mind, b is positive, then there is a positive sign, and b is negative, there is a negative sign, but otherwise minus 2c in both the cases. So this is to note. Okay, so in the next class we'll discuss different form of the function, how we can avoid loss of significance in those cases. Okay, thank you.